Okay, 1.6, we're going to be talking about polynomial and rational functions. So first of all, polynomial functions. We want to define these. We want to get a little bit of the vocabulary going. So a polynomial function, we define this to be written as a sub 0 plus a sub 1, x to the first power, a sub 2, x to the second, and so on. That's where the dot 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 comes from, all the way up to some a sub n x to the n power. All right, so this can be intimidating for students. All right, I get that when you see this definition, it looks intimidating. Why we write it like this is basically we want to be able to identify that all of these coefficients are the numbers, the constants out in front of each and every one of these terms. All right, we think of terms as being separated by addition signs, and they make up whatever the polynomial is. All right, so intimidating definition, I get that. All of our exponents, we have x to the first power, x to the second power, there would be an x to the 0 power, could be sitting next to this number. These first three, if I just isolated those and cut them off from the rest of this polynomial, that is what we refer to as a quadratic function, right? ax squared plus bx plus c is nice, all right? But in our case, we can have higher powers than just x to the second power. So to take that into account, we write this out, and it's scary, but don't get intimidated by this. All right, seriously, when we get numbers plugged in here, it's going to make a whole lot more sense. We're going to do an example in just a second. Remember, the exponents on the variable, in our case, x is the variable. These are going to be whole numbers, right? Like 0, 1, 2, etc. So you're not going to have anything weird up there like radicals or fractions or decimals, anything like that going on in the exponent, no negative exponents. But the numbers in front, all of these coefficients as we call them, those just have to be any number, right? They can be positive, negative, 0, whole numbers, decimals, fractions, basically whatever. All right. Next up, the degree of a polynomial is going to be the highest power on x, or whatever our variable is. Now, individual terms have their own degrees, and we're going to see this in a second and identify them, and then the overall polynomial has its degree. Now, typically, we like to write these in descending order. I'm not sure why we didn't define it in descending order, but at the bottom, you can see we have the highest power first, and then this would be the next highest power next, all the way to the second, the first, and then x to the 0 could be hanging out here next to this constant. All right, so the constant always comes last in descending order. Now, if we've written it in descending order, then the leading term is just going to be the first one. The leading coefficient, we already defined coefficient to be the number in front, so the leading coefficient would be the number in front of the first term. So let's jump into a number example here. It'll make more sense of all that stuff as we get going on it. So our function is defined at the top. Let's first rewrite this in descending order. So we're looking for the highest power of x. That term comes first. So in our case, x to the fourth is going to be the highest. So I'm just moving that term in the front. Now x cubed is the next highest power of x. And then the 5, a constant, always comes last. Okay, the degree of each term is the power on, just isolating, looking at the 4x to the fourth. Its degree is going to be 4. X cubed, its degree is going to be 3. And a constant is going to have degree 0. Now why that is because we could think 5 times 1 means the same thing as 5. But instead of 5 times 1, I could write 1 as x to the 0 power. All right, x to the 0 power from our exponent section equals 1. So that's why constants always have a degree of 0. I'm going to get rid of that so it doesn't confuse us anymore. Now, the overall degree of the polynomial is the highest degree on any individual term. So since we've rewritten it in descending order, it's going to be just the degree of that first term. You don't add these together. Please don't add them together. All right, it's not going to be 7 in this case. It's only going to be 4. Now, our leading term, we just need to know where to look. It's going to be the very first term. So we'd say it's going to be 4x to the fourth power. And the leading coefficient, that's the number out in front, is going to be 4. All right, next up, to wrap up this video, let's talk about even power functions, odd power functions, and end behavior, how we can look at a polynomial and find the end behavior for that entire polynomial. Okay, so we define an even power function as just being something pretty basic wherever we have x raised to some even power. All right, so one we've already seen is y equals x squared in the quadratic section. And you may recall that graph, it looks like this, right? The right side goes up, the left side goes up. We call that a parabola. An odd power function, we have seen one of these as well. We define it to be x raised to any odd power. So one we have already discussed a little bit is when we have x raised to the first power. We can think of that as a linear function, a straight line. And in this case, it would have a y-intercept of 0, but a slope of 1, right? Y equals mx plus b. And notice where the ends go, the tails. It goes up to the right and down to the left. On even power functions, both tails go up to the left, up to the right. So those are the basics we want to kind of get down here. Now, let's discuss real quickly if we looked at higher powers, like if we wanted to see y equals x to the fourth power. Now, the basic shape is going to be the same. It's a little bit closer to the x-axis in the middle and a little bit steeper on the outside. But again, both tails go up. That's the important thing. As we're thinking about power functions, both tails go up to the left, up to the right. That's what you want to get down and take away from this. Now, odd power functions, you may be saying, what's, say, y equals x cubed look like? Well, it goes up to the right, but it goes down to the left and has that basic shape. So what you want to have down is for odd power functions, the tails go up to the right and down to the left. Yeah. Those are the basics for power functions, what we want to get down. Now, these tails could flip upside down and go the opposite direction if there were, say, a negative leading coefficient, a negative number out in front. That would be a vertical reflection, thinking back to our transformation section. So this begs the question, thinking about the polynomial we're actually dealing with. If I want to know what the end behavior is, or sometimes our book calls this the long run behavior, what they're asking about is where do those tails go at the end? And I'll tell you exactly where we want to look for that. You want to look to the leading term, which we already identified over on the left-hand side. That's going to dictate the overall end behavior for the entire polynomial. I know there are 3 terms in this polynomial, but the leading term, that highest power of x, that's going to dictate what's going to happen at the ends. Where do the tails go? So in our case, if I asked you to graph, hey, what's y equals 4x to the fourth power look like? Well, I already graphed the x to the fourth power up there, just above us in red. It's an even power. That 4 out in front, that leading coefficient, isn't going to flip it upside down. So on the right-hand side, it goes up, and the left-hand side, it goes down. Now, another way to write this is with limits. We can say the limit as x goes to infinity, as we move off to the right-hand side of our function f of x, it goes up. So which y value do we get close to? So hopefully we can understand maybe the first time we've seen limits, but as the limit as x approaches infinity, that says as we go off to the right-hand side, as our x values increase without bound, what happens with our y values? Well, tracing this up, it goes up, 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 when that goes towards positive infinity. Oh, I've messed this up. X to the fourth power, the left-hand side does not go down. It's supposed to go up as well. All right, so now that I've messed that up, I'm not going to redo this. Technology already failed me once, and I'm redoing the video for the second time right now. So let's take a look at the limit as x approaches negative infinity. That says as we go off to the left-hand side, as our x values increase in the negative direction without bound, what happens with our y values? Well, as I trace this up, it goes up, up, up forever, and that's going to be y values of positive infinity out that direction. So I hope this helps out. Sorry I made a mistake there with drawing it in the wrong direction. Tried to correct that to finish it up. Good luck.